Have you ever stopped to think about how the world around us is made of invisible things? That's right. A single cubic centimeter of air contains no less than 20 quintillion atoms, and just in your body, there are about 7 times 10 to the 27th power of them. A number so big it doesn't even fit in your head. These tiny building blocks, the atoms, are in everything, in the air, in objects, in your breakfast, and yet we spend our entire lives surrounded by them without ever really seeing them. Until recently, no one had even managed to observe them directly. Today, the idea is bold. We're going to get as close as possible to this fascinating and almost unbelievable reality, the world of atoms. Let's dive deep into a journey toward the smallest unit of matter that makes up everything around us, starting with our hair. Thanks to a video created by CERN, the world's largest particle physics research organization, we take the first step. Follow along. We're entering the interior of a hair cell. It's made up of macrofibrils, which in turn are formed by a tangle of microfibrils. And they're also made of even smaller fibers. At the center of it all, we find the protein keratin, a long molecule made up of interconnected chains of amino acids. These amino acids, in turn, are made of atoms such as sulfur, nitrogen, oxygen, carbon, and hydrogen, some of the simplest and most common atoms in the universe. But how do we represent an atom? Usually with a very familiar image. A central nucleus made of protons and neutrons, with electrons spinning around like planets orbiting the sun. That's the famous planetary model. Except, spoiler, that model is completely wrong. Yes, as useful as it may be for teaching, it's a distortion of reality. In fact, that model should be thrown away for 2 very important reasons. The first has to do with the proportions inside the atom. To give you an idea, the nucleus of an atom is about 100,000 times smaller than the atom itself. If the nucleus were the size of a 1 millimeter ball, the electrons would be almost 100 meters away. This means that 99.99999% of an atom's volume is simply vacuum, empty space. So much empty space that if all of humanity were magically compressed to eliminate all that vacuum between atoms, our entire species would fit inside a cube the size of a dice, weighing 500 million tons. Terrifying, maybe? But that will never happen. The repulsive forces that keep matter, as we know it, prevent atomic particles from getting that close to one another. Still, interestingly, there are places in the universe where something like this does happen. Stars called white dwarfs and neutron stars are made precisely of this type of ultra-compressed matter. The second major reason why the planetary model of atoms must be abandoned, perhaps the most important of all, it simply doesn't reflect the true nature of subatomic particles. When we dive below the scale of 1/10 of a nanometer, the laws of our everyday world stop working. Matter, its movement, its logic, everything changes. We enter a strange, unpredictable territory, the realm of quantum mechanics. Let's start by making one thing clear. If we want to represent electrons in a way that's closer to reality, we need to abandon the idea that they orbit the nucleus like tiny, well-behaved planets. The truth is that electrons are incredibly fast, nearly impossible to capture true ghosts of matter. Even under normal conditions, a single electron makes, on average, 6.6 quadrillion turns per second around the nucleus. That means it reaches a speed of about 2,400 kilometers per second. It's so fast it could go from New York to Los Angeles and back many, many times in a single minute. Still, this impressive speed isn't even 1% of the speed of light. But here's the big plot twist. Electrons aren't really spinning. They don't orbit like satellites around the Earth. When we use the idea of speed, we're actually relying on a simplified model, Bohr's model, which basically exists so we don't go insane trying to understand the subatomic world. Instead of circular motion, it's more accurate to talk about energy levels, and more importantly, to understand that in this microscopic universe, the idea of knowing exactly where a particle is simply doesn't make sense. As strange as it sounds, electrons don't have a defined position. They aren't little balls with an exact location. They're dimensionless particles, and it's impossible to know both where they are and how fast they're moving at the same time. That's one of the consequences of Heisenberg's famous uncertainty principle. If this topic interests you, check out our video that explains these quantum oddities in more detail. But there's more. When we dive even deeper into these atomic scales, we discover that matter, including electrons, also behaves like waves. In other words, they can act both as particles and as waves. Bizarre? Very. But that's exactly what makes this universe so fascinating. To handle this complexity, scientists prefer to represent electrons not as tiny dots spinning around, but as diffuse clouds known as wave functions. And no, these clouds are not trails left by electrons in motion, like cars speeding down a highway. These clouds are the electrons themselves, occupying all that fuzzy space. These representations, these electron clouds, are, to this day, the best visual way we have to try to understand where electrons might be. They show regions of higher or lower probability of finding an electron when we observe them with our instruments. Inside these clouds, electrons seem to jump from one place to another. One moment they look like localized particles, the next they dissolve again into the quantum haze. It's a true game of hide and seek. By nature, these hazy zones where electrons can appear are called atomic orbit. They follow this half-particle, half-wave behavior, revealing the regions where electrons prefer to show up when we try to observe them, always randomly, always unpredictably, as if each appearance were a surprise. And things only get stranger. When we talk about atomic orbitals, we need to understand an almost unbelievable truth about electrons. They are everywhere at the same time within those regions. Yes, that's right. Instead of being located in a specific point, electrons are simultaneously present in all possible points around this nucleus. They occupy the space as if they were completely spread throughout it, and they only choose a place when we try to observe them. You can imagine orbitals as a kind of map of possibilities, a territory where the electron could be, but where the chance of finding it varies depending on the region. The denser the cloud area, the greater the probability of the electron showing up there. But here's the curious part. Because of the bizarre laws of quantum mechanics, there's always a small chance it could show up even outside those most likely zones, practically anywhere around the atom. In other words, in the absence of any measurement or external disturbance, the electron is the orbital cloud itself. It's trapped inside an invisible web whose shape and energy are determined in part by the nucleus of the atom. This nucleus works like an invisible electric field, imposing limits on the electron's possibilities, like a force field that defines where it can or cannot exist. But how do we know the shape of these clouds? The answer comes from two paths: super complex mathematical equations and lots of experimentation. Over time, after thousands and thousands of measurements, we realized that electrons show up more often in certain regions, and by accumulating these observations, we managed to draw these probability clouds, like pointillist paintings made of countless dots that together formed a blurry image of the electrons' presence. And here comes a visually beautiful and scientifically incredible part: the shapes of the orbit. Depending on the electron's energy level, these clouds organize themselves into surprising shapes, almost like exotic flowers, varying in fascinating ways. What you see on screen now are precisely the different possible shapes of these orbitals, and all of them belong to the simplest atom in the universe: hydrogen. It has only one proton in its nucleus and a single electron around it. At the lowest energy levels, this electron appears in an almost spherical cloud, but as it gains more energy, new shapes emerge: double spheres, elongated lobes, curious symmetries, and even shapes that resemble belts around the nucleus. These shapes actually represent the statistical boundaries of where the electron can exist inside the atom. It's as if each shape were a small energy prison, defining the possible spaces for the electron to manifest. And these prisons aren't fixed. If the electron gets sufficiently excited, meaning it receives energy, it can make a quantum leap to a higher energy level and completely change shape. And this is where one of the most important ideas in quantum physics comes in. The atomic world is discontinuous. Electrons don't change energy. Little by little, like walking up a gentle slope, they jump from one level to another without passing through the middle, like climbing stairs, not a ramp. That's why we say that things at this level are quantized. Only certain values are allowed, period. An electron's wave function can only take on certain specific forms. Others are simply impossible. In short, the components of the atom live in a universe of jumps, of discrete rules, where only certain combinations are allowed. And it's precisely these combinations, these patterns of energy and shape, that determine the beautiful and complex atomic orbitals we studied today. To make things even more interesting and a bit more chaotic too, we can ask, how does this whole story work in heavier atoms with far more electrons than hydrogen? Well, roughly speaking, it becomes an even bigger mess. With each new proton added to the nucleus, a new electron enters the game around it, and that changes everything. The strength with which the nucleus attracts these electrons increases, and the shapes of the electron clouds transform. Those quantum flower petals we saw before gain even more variety, because the new orbitals fit together in increasingly complex ways. But here's a surprising detail. When we add electrons, they don't stack up one on top of the other like layers of an onion. Instead, they interpenetrate like clouds, mixing inside one another. This means that even if an atom has dozens or even hundreds of electrons, its size doesn't grow proportionally. Want an example? The gold atom has 79 electrons, while carbon has only 6. By the logic of the onion, gold should be about 10 times bigger, but in practice, it's only about twice as big. That happens because gold's 79 electron clouds overlap, occupying almost the same space as if they were layers of smoke filling the same room. In other words, adding protons, neutrons, and electrons drastically changes the behavior and properties of the atom, but changes very little of its physical size. Now, to organize this atomic chaos, nature relies on a fundamental rule: the Pauli exclusion principle. Without getting too technical, this rule says that two electrons cannot occupy the exact same state within the same orbital. This means that even while sharing the same space, they always need to have different configurations. This principle is essential to bring order to all this complexity. And as chaotic as it may seem, there is a certain elegance in this apparent chaos. Because, in the end, what determines how atoms connect with each other, how they bond to form molecules, materials, living beings, are only the electrons in the outermost layer. The so-called valence electrons, they're the ones who decide if two atoms will get along and bond or not. It's as if they were the basic vocabulary of chemistry, the set of words that allows atoms to talk to each other. And spectacularly, it's these outer electrons that define all the properties of matter, whether it's solid, liquid, or gas, whether it conducts electricity or insulates, whether it's rigid, flexible, shiny, opaque, colorful, transparent. In other words, it's orbitals and electrons that make a carbon atom. Always carbon, whether it's found in your body, in a starfish, or in a pencil tip. It will behave exactly the same way. And want to know the most impressive part? If right now there were a science class happening on the other side of the galaxy, aliens would be studying the same atomic elements we do, because the periodic table is universal. Wherever you go in the cosmos, hydrogen will be hydrogen, oxygen will be oxygen, and carbon will always be the carbon that connects us. Now, going back to the question from the beginning, have we actually ever seen an atom? Or is everything we've shown so far just simulations, models, and illustrations? Well, the answer to have we ever seen an atom is, in a way, yes. Not yet in the same way we see an apple or a tree, of course, but we've been able to observe them indirectly, which is already a huge achievement for science. For example, we can reconstruct the shapes of electron orbitals by analyzing the color of light electrons emit when they change energy levels. These emission patterns give us clues about where electrons are most likely to be, as if we were tracing the outlines of the cloud. Of course, it's all much more complex than that, but in general, that's the idea. In 2008, a team of Swedish scientists managed to record orbital variations over time, creating a kind of animated map of electron behavior. What you're seeing on screen in 2 dimensions is a visual interpretation of that data, the result of indirect but incredibly precise measurements. In addition, we can also see individual atoms using a special tool called a scanning tunneling microscope. With it, we can capture images magnified up to 100 million times, revealing the arrangement of atoms on the surface of materials like in a crystal, for example. And want to see a curious application of this? IBM created the world's smallest animated film using this technology. The movie was made by moving oxygen atoms, one by one, with the help of the microscope. Then, scientists took successive pictures of each movement and created a stop-motion animation. Each little dot you see on screen is a real oxygen atom, and the ripples around them show the quantum behavior of the electrons. Until recently, this kind of image was the most science could achieve when it came to seeing an atom. But then, a researcher named Anita Stodona came onto the scene and took things a step further. She found a creative way to, let's say, photograph the shadow of hydrogen's wave function. And take a look at what she got. That grainy, mysterious blob you're seeing now on screen is considered the first direct image of the inside of an atom. It shows the spatial distribution of the electron's wave function in a highly excited state of hydrogen. In other words, it's as if we were seeing the density of the electron cloud, where the electron has more or less chance of being. But as extraordinary as this image is, it still doesn't reveal everything. There's one aspect of electrons we may never be able to truly visualize. Spin. Spin is an intrinsic property of electrons, a kind of internal rotation, but not a rotation in the traditional sense. And more, it's a quantized property, meaning it can only take on two possible values. It's as if the electron were a tiny, mysterious magnet, able to point only up or down, left or right, even though, in practice, it has no volume or surface to spin. By now, you must be thinking, how do we represent a particle that has no size, no shape, no defined position, but does have mass, energy, spin, and still behaves like a cloud? Yeah, it's pretty complicated. But before we wrap up, here's a curious fact. The protons and neutrons that form the nucleus of an atom aren't indivisible. Inside them, there are even smaller particles, known as quarks, are 10,000 times smaller than the nucleus. So small that proportionally, you are 100 times bigger to a quark than the nearest star to the sun is to you. Yes, in this invisible universe, we are practically cosmic giants. And the most amazing part, this absurdly small world is everywhere, around us and inside us. It's a territory that keeps expanding in discoveries and still holds many mysteries. If you want to keep exploring this journey and understand how atoms formed long before Earth even existed in the stars that forged them, this video here tells that fantastic epic. Link in the pinned comment. Did you enjoy the video? Want to keep exploring the mysteries of the universe? Check out our exclusive ebooks, perfect for anyone who wants to dive even deeper into this journey of knowledge. The ultimate guide to the solar system. Discover incredible images, fascinating curiosities, and accessible explanations about the planets, their moons, the sun, and our beloved Earth.